125 microseconds, 0.125 milliseconds. This is what we have in regular coding to 64 kilobits per second. The ADPCM technique also does this. But look what happens to the quality. If we go down to 16 kilobits per second, the mean opinion score drops down to 2.4. So we're getting down close to poor quality speech. Now, if we crank the bits per second up to 40 kilobits per second using the same technique, then the mean opinion score goes up to 4. So that's equivalent to regular toll quality speech. Now, that's not really a big improvement. Instead of using 64 kilobits per second, we're going to use 40 kilobits per second. That's hardly any voice compression at all. Like, it's less than 2 to 1. So this technique has been used, but we've got better stuff. Most of the other techniques are based on something called linear predictive coding, LPC. And this is based on building a mathematical model of what somebody's throat looks like, and then predicting what is going to come out next based on what came out recently. And I'm talking on a millisecond by millisecond basis here. And the idea is, if you get a real good model of the throat, then your prediction of what's going to come out next based on what came out recently is going to be quite good. And what we do is we run this predictor, and then we compare it to what actually happened and subtract the two. And that's the difference between our prediction and what actually happened. It's called the error signal. And we transmit the error signal to the far end. We run the same predictor at the far end and use the error signal to correct its prediction to regenerate what actually happened. And you see, if your predictor is real good, then the error signal is going to be very small, and so you don't need a lot of capacity to transmit the error signal. This is how all of the newer voice compression techniques work. On our chart, the second line, G.723, uses a technique called algebraic code-excited linear prediction. And you can see that the bit rate goes down quite significantly, 5.3. That's what, 12 to 1 compression. And the mean opinion score is 3.6. So this is almost toll quality speech, halfway between toll quality and the next level down. But what does it cost us? 37.5 milliseconds of delay. And as we're going to see on the next couple of slides, this is significant because there's a maximum specification for the maximum allowed end-to-end delay, and it's usually thought to be 200 milliseconds, absolute maximum allowed, and right here the coding process puts almost 40 milliseconds of delay in. And let's not forget the decoding process at the other end, adding another 40 milliseconds of delay. So right here, the compression technique adds in 80 milliseconds of delay. So essentially, this eats up half of our delay budget. So we might not be able to use this technique. On the third line, you'll see that if we crank the bit rate up to 6.3 kilobits per second using a slightly different technique, that's almost exactly 10 to 1 compression, then the mean opinion score goes up to 3.9, which is pretty close to toll quality speech. So using the G723 codec at 6.3 kilobits per second, it gets us toll quality speech, but it eats up half of our delay budget. Since the G.723 codec introduces such a large delay, we might want to keep looking a little bit longer for a better technique. And if we look at our chart again, the G.728 codec, the second one from the bottom, it allows us to reduce the bit rate down to 4 to 1, so 16 kilobits per second, using a type of code-excited linear prediction. And it's got hardly any delay, 0.625 milliseconds, which is pretty much negligible. And it gets us a mean opinion score of 3.6. So that's real close to toll quality speech. And then if you look at the bottom row, G.729, this lets us get the bit rate down to 8 kilobits per second. So that's 8 to 1 compression. introducing a moderate amount of delay, 15 milliseconds, and the toll quality speech at 3.9 opinion score. So these would be the two that we would be interested in looking at if we decided to implement compression on our voice over IP system. If delay was a big problem and we couldn't use a codec that introduced delay, then we'd look at the G.728. If we had room in our delay budget to use a coder that introduces a moderate amount of delay, then we'd certainly take a look at the G729 because it gives us 8-to-1 compression at toll quality speech. All of this discussion of coding and compression is one thing, but a larger question is, do you want to use compression? A friend of mine that I've been working with for years has a company that's in the quality of service testing business, and they build systems that they sell to telecommunications carriers to be able to do quality of service measurements on their networks. And I was talking to him just a while ago, and he said, we love voice compression because it causes no end of trouble, and so it generates a lot of business for our testing equipment. The problem with doing voice compression is not only the question of getting the algorithm working at one end and the same one running at the other and getting them synchronized so that what you put in here comes out over there. Besides that problem is that it makes the communications hypersensitive to packet loss. So generally what we would recommend is when you're first starting off designing a voice over IP system is you use the G711 codec, 64 kilobits per second, and no variable rate options. Just have it spit out 64 kilobits per second all the time. Get that working, and once it's working, then you can start fooling around with compression to see if you can get that working. But we certainly wouldn't recommend that you design a system from the start to use compression because you're asking for a lot of debugging and trouble up front. It would be better to get it working with the basics first and then put compression on second. Another element that affects voice quality is delay. And the main reason for this is echoes. Always, when you're making phone calls, there are echoes happening. There's an echo coming off of the telephone switch, and there's an echo coming back off of the far end telephone. And on telecommunication networks, we put echo cancelers in place to cancel out these echoes so you don't actually hear them. And the idea is that what we do is we listen to what went out and wait to hear if it comes back again and mathematically subtract it off when it comes back so then you don't hear it. The implication of that is that there's a maximum length of time allowed for an echo to happen. Because if we set up a system where it remembers what went out and it keeps listening for it coming back so it can mathematically subtract it off, well, how long is it going to remember for before it moves on to the next chunk of what came out of your throat? And in the telecommunication system, there's a maximum length of the echo canceller, how long it's able to remember for before it moves on. It's kind of a sliding window sort of thing. And so what happens is if the echo comes back within the length of the echo canceller memory time, then it will cancel it off and you won't hear it. But if the echo takes longer to come back from the far end than the length of the echo canceller, then you are going to hear the echo. And on a voice over IP system, the absolute maximum is 200 milliseconds, and that would be a hard limit. We recommend that the maximum delay that's designed into a system is 150 milliseconds. So that would be our design maximum. Now you start thinking back to our codecs, and if you think of the G723 codec that introduced 40 milliseconds of delay, and our design maximum is 150 milliseconds, well, right there we've eaten up half of the allowed delay budget. So then the next question would be, are there additional sources of delay besides just the delay in the coding technique at each end? The additional sources of delay could be a delay caused by equipment,